This presentation is delivered by the Stanford Center for Professional Development.
So, welcome back. And what I want to do today is continue our discussion of the EM algorithm. And in particular, I want to talk about the EM formulation that we derived in the previous lecture and apply it to the mixture of Gaussian's model, apply it to a different model called the mixture of naive Bayes model. And then a large part of today's lecture will be on the factor analysis algorithm, which will also use EM. And as part of that, we'll actually take a brief digression to talk a little bit about sort of useful properties of Gaussian distributions. So just to recap where we are, in the previous lecture, I started to talk about unsupervised learning, which was machine learning problems where you're given an unlabeled training set comprising M examples, say, right? And so the fact that there are no labels, that's what makes this unsupervised learning. And so, you know, one problem that I talked about last time was, what if you're given a data set that looks like this, and you want to model the density P of x from which you think the data had been drawn. And so with a data set like this, maybe you think it's a mixture of two Gaussians, and start to talk about an algorithm for fitting a mixture of Gaussians model, right? And so concretely, we said that we would model the density of x, P of x, as sum over z, P of x given z times P of z, where this latent random variable, meaning this hidden random variable z, indicates which of the two Gaussian distributions each of your data points came from. And so we had, you know, z was multinomial with parameter phi, say, and x conditioned on it coming from the jth Gaussian was given by that by a Gaussian with mean mu j and covariance sigma j. Right? So I guess at the beginning of the previous lecture, I just talked about a very specific algorithm that I sort of pulled out of the air for fitting the parameters of this model, for fitting the parameters phi, mu, and sigma. But then in the second half of the previous lecture, I talked about what's called the EM algorithm, in which our goal is maximum likelihood estimation of the parameters. So we want to maximize in terms of theta, you know, this sort of usual, right, maximum log likelihood, well, parameterized by theta. And because we have a latent random variable z, this is really maximizing in terms of theta, sum over I, sum over z, P of xi, zi, parameterized by theta. Okay. So using Jensen's inequality last time, we worked out the EM algorithm in which in the E step, we would choose these probability distributions Qi to be our posterior, you know, on z given x and parameterized by theta. And in the M step, we would set theta to be the value that maximizes this. Okay, so these were all formulas that we worked out last time. And the cartoons that I drew was that you have this log likelihood function, L of theta, that's often hard to maximize. And what the E step does is choose these probability distribution Qi's, and in the cartoon I drew, what that corresponded to was finding a lower bound for the log likelihood, and then horizontal axis is theta, and then the m step you maximize the lower bound, right? So maybe you were here previously until you jump to the new point, the new maximum of this lower bound. Okay, and so this little curve here, right? This lower bound function here, that's really, you know, the right hand side of that argmax. Okay, so this whole thing in the argmax, if you view this thing as a function of theta, this function of theta is a lower bound for the log likelihood of theta. And so in the m step, we maximize this lower bound, and that corresponds to, you know, jumping to this new maximum of the lower bound. So it turns out that in the EM algorithm, so why do we bother with the EM algorithm, right? It turns out that very often, and this will be true for all the examples we see today, it turns out that very often, in the EM algorithm, maximizing the m step, so performing the maximization in the m step will be tractable and can often be done analytically in closed form. Whereas if you were trying to maximize this objective, we try to, you know, take this formula on the right, this maximum likelihood objective, was to take this one on the right and set its derivatives to 0 and try to solve, you find that you're unable to obtain a solution to this in closed form, this maximization. Okay? And so a concrete example of that is that you remember our discussion on exponential family models, right? It turns out that if x and z, you know, this is jointly, I guess, lie in an exponential family. So if p of x comma z parameterized by theta, if this is an exponential family distribution, which it turns out to be true for the mixture of Gaussian's distribution, then it turns out that the m step here will be tractable, and the e step will also be tractable, and so you can do each of these steps very easily. Whereas you're trying to perform this original maximum likelihood estimation problem, this one, right, would be computationally very difficult. If you were to set the derivatives to 0 and try to solve for that analytically, you won't be able to find an analytic solution to this. Okay. So what I want to do in a second is actually take this view of the EM algorithm and apply it to the mixture of Gaussian's models. I'm going to take these E steps and M steps and work them out for the mixture of Gaussian's model. But before I do that, I just want to say one more thing about this broader view of the EM algorithm. It turns out that there's one other way of thinking about the EM algorithm, which is the following. I can define an optimization objective, J of theta comma q. I'll define it to be this. This is just a thing in the argmax in the m step. Okay. And so what we proved using Jensen's inequality is that the log likelihood of theta is greater than or equal to j of theta comma q. So in other words, we proved last time that for any value of theta and q, the log likelihood upper bound is j of theta and q. And so just to relate this back to sort of yet more things that you already know, you can also think of, hope you remember coordinate ascent. Right, hope you remember our discussion a while back on the coordinate ascent optimization algorithm. So what you can show, I won't actually show this, you can sort of just take our word for it and think for it at home if you want, that EM is just coordinate ascent on the function j. So in the E step, you maximize, you know, with respect to q, and in the M step, you maximize with respect to theta. Okay, so this is sort of another view of the EM algorithm that shows why it has to converge, for example, at least in the sense of j of theta comma q having to monotonically increase on every iteration. Okay. So, right. So what I want to do next is actually take this general EM machinery that we worked out and apply it to the mixture of Gaussians model. Before I do that, let me just check if there are questions about, the EM algorithm as a whole. Okay, cool. So let's go ahead and work out the mixture of Gaussians EM. Right. MOG, that's my abbreviation for mixture of Gaussians. So in the E step, we have to work out those Q distributions, right? In particular, we have to work out, so Q is the probability distribution over the latent random variable Z. And so in the E step, we're going to figure out what is, I need to compute what is Q of Zi equals J. You can think of this as my writing, P of Zi equals J, right, under the Q distribution. That's what this notation means. And so the EM algorithm tells us that, let's see, Q of J is the posterior probability of Z being a value J, and given xi and all your parameters. And so, well, the way you compute this is via Bayes' rule, right? So that is going to be equal to P of xi given Zi equals J times P of Zi J divided by right? That's sort of by Bayes' rule. And so this, because xi given Zi equals J, this was a Gaussian with mean mu J and covariance sigma J. And so to compute this first term, you plug in the formula for the Gaussian density there with parameters mu J and sigma J. And this because Z was multinomial, right? With parameters given by phi, and so the probability of Zi being equal to J is just phi J. And so you can substitute these terms in, and similarly do the same thing for the denominator, and that's how you work out what Q is. Okay. And so in the previous lecture, this value, the probability that Zi equals J under the Q distribution, that was what I denoted that as Wij. So that would be the E step. And then in the M step, we maximize with respect to all of our parameters. This, well, I seem to be writing the same formula down a lot today. Right? And so, just to be completely concrete about how you do that, right? So if you do that, you end up with, so plugging in, the quantities that that becomes this. Let's see. Right, and so this is completely concrete about what the M step is doing. So in the M step, that was, I guess, Qi of Zi being equal to J. This inner summation, sum over J, is the sum over all the possible values of Zi. And then this thing here is my Gaussian density. So I guess this thing, well, this first term here, right, is my p of xi given zi, and that's p of zi. Okay? And so to maximize this with respect to, so you want to maximize this with respect to all of your parameters, phi, mu, and sigma. So to maximize with respect to the parameter mu, say, you would take the derivative with respect to mu and set that to 0. And you would, and if you actually do that computation, you would get, for instance, that that becomes your update to mu j. Okay, just so I want to. The equations aren't unimportant. All of these equations are written down in the lecture notes. I'm writing these down just to be sort of completely concrete about what the m step means. So write down that formula, plug in the densities you know, take derivative, set to 0, solve for mu j. And in the same way, you set derivatives equal to 0 and solve for your updates for your other parameters, phi and sigma as well. Okay. Yeah. Well, and then just point out just one little tricky bit for this that you hadn't seen before that most of you probably already know, but I just mentioned is that since phi here is a multinomial distribution, when you take this formula and you maximize it with respect to phi, you actually have an additional constraint, right? That the sum over I, sum over j, phi j must be equal to 1, right? So again, in the m set, want to take this thing and maximize it with respect to all the parameters. And when you maximize this with respect to the parameters phi j, you need to respect the constraint that sum of j phi j must be equal to 1. And so, well, you already know how to do constraint maximization, right? We talked about the method of Lagrange multipliers and the generalized Lagrangian when we talked about support vector machines. And so to actually perform the maximization in terms of phi j, you construct the Lagrangian, which is, right, so that's the equation from above. I'm going to denote the dot, dot, dot plus beta times that, where this is the Lagrange multiplier. And this is, this is your optimization objective. And so to actually solve the parameters phi j, you would set the parameters of this of the Lagrangian to 0 and solve. Okay, and then if you then work for the math, you get the appropriate value to update the phi j's to. Which I won't do, but all the full derivations are written on the lecture notes. So I won't do that here. Okay, and so and so if you actually perform all these computations, you can also verify that I sort of just wrote down a bunch of formulas for the EM algorithm at the beginning of the last lecture. I said, for the mixture of Gaussians model, I said for the EM, here's the formula for computing the WIJs, and here's the formula for computing the mu's and so on. And this derivation is where all of those formulas actually come from. Okay. Questions about this? Yeah. Oh. I see. Yeah. So it turns out that yes, there's also a constraint that the phi j's must be greater than 0. It turns out that if you want, you could actually write down the generalized Lagrangian, incorporating all of these constraints as well, and you could solve taking into account these constraints. It turns out that in this particular derivation, actually, it turns out that very often when you find maximum likelihood estimate for multinomial distribution probabilities, it turns out that if you ignore this constraint and you just maximize the formula, you actually, luckily, you end up with values that actually are greater than or equal to 0. And so if even ignoring this constraint, you end up with parameters that are greater than or equal to 0, that shows that that must be the correct solution, because adding that constraint won't change anything. So yeah, so this constraint is important, but it turns out if you ignore this and just do what I wrote down, you actually get the right answer. Cool. Okay. Great. So let me just very quickly talk about one more example of a mixture model. And the motivating example for this is, imagine you want to do text clustering, right? So someone gives you a large set of documents and you want to cluster them together into cohesive topics. I think I mentioned the news website, news.google.com. That's one application of text clustering, where you might want to look at all the news stories about today, all the news stories written by everyone, written by all the online news websites about whatever happened yesterday. And there'll be many different stories on the same thing, right? And by running an algorithm like a text clustering algorithm, you can group related documents together. Okay. So how do you apply the EM algorithm to text clustering? Well, and I want to do this to illustrate an example in which you run an EM algorithm on discrete valued inputs, where the training examples xi are discrete valued. So what I want to talk about specifically is the mixture of naive Bayes model. And depending on how much you remember about naive Bayes, I talked about two event models. One was the multivariate Bernoulli event model. One was the multinomial event model. Today I'm going to use the multivariate Bernoulli event model. If you don't remember what those terms mean anymore, don't worry about it. I think the equations will still make sense. But in this setting, we're given a training set, say x1 through xm. So we're given, say, m text documents, where each xi is is 0, 1 to the n. So each of our training examples is an n-dimensional bit vector, right? So this was the representation where xi j was, it indicates whether word j appears in document I, right? So, and let's say that we're going to model zi, our latent random variable, meaning our hidden random variable zi will take on two values 0, 1. So this means I'm just going to find two clusters. You can generalize this to k clusters if you want. Okay. So in the mixture of naive Bayes model, we assume that zi is distributed Bernoulli with some value phi, so there's some probability of each document coming from, cluster 1 or from cluster 2. And we assume that the probability of xi given zi, right, we'll make the same naive Bayes assumption as we did before. Okay. And more specifically, well, excuse me. Right, okay. And so more specifically, probability of xi equals 1 given zi equals, say, 0 will be given by a parameter phi subscript j given z equals 0. And so if you take this chalkboard and if you take all instances of the alphabet z and replace it with y, then you end up with exactly the same equations as that written down for naive Bayes, like a long time ago. Okay. And I'm not actually going to work out the mechanics of deriving the EM algorithm, but it turns out that if you take this joint distribution over x and z, and if you work out what the equations are for the EM algorithm for maximum likelihood estimation of parameters, you find that in the E step, you compute, let's say these parameters, these weights, Wi, which are going to be equal to, say, a posterior distribution of z being equal to 1, conditioned on xi, parameterized by, your phi's, and given your parameters. And in the M step, okay, and those are the equations you get in the M step. And again, the equations themselves aren't too important. Just want to convey. I'll give you a minute. I'll give you a second to finish writing, I guess. And those you that finish writing, take a look at these equations and see if they make intuitive sense to you. Why these three equations sort of sound like they might be the right thing to do. Yeah. Say that again. Oh yes, thank you. Right. Z. Sorry, just everywhere I wrote Y, I actually meant Z. Yeah.
Just initialize phi's with 0 in the first place?
No, so what is it? Normally you initialize phi's to be something else, say randomly. Yeah, so just like in naive phase, we saw 0 probabilities is a bad thing. So for the same reason, you try to avoid 0 probabilities. Yeah. Okay. And so just the intuition behind these equations is, in the E step, Wi's is you're going to take your best guess for whether the document came from cluster 1 or cluster 0. Right? This is very similar to the intuitions behind the EM algorithm that we talked about in the previous lecture. So in the E step, we're going to compute these weights that tell us, do I think this document came from cluster 1 or cluster 0? And then in the M step, I'm going to say, this numerator is a sum over all the elements of my training set of sort of informally, right? Wi is 1 if I think the document came from cluster 1, say. And so this will be essentially sum up all the times I saw word J in documents that I think are in cluster 1. And these are sort of weighted by the actual probability I think it came from cluster 1. And then I'll divide by, again, if all of these were 1s and 0s, then I'd be dividing by the actual number of documents I had in cluster 1. So if all the Wi's were either 1 and 0s, then those would be exactly the fraction of documents that I saw in cluster 1, in which I also saw word J. Okay? But in the M algorithm, you don't make a hard assignment decision about is this in cluster 1 or is this in cluster 0. You instead represent your uncertainty about cluster membership with the parameters Wi. Okay? It actually turns out that when we actually implement this particular model, it actually turns out that by the nature of this computation, all the values of Wi's will be very close to either 1 or 0. So it'll be numerically almost indistinguishable from 1s and 0s. This is property of naive Bayes. If you actually compute this probability for almost all the documents, you find that Wi is either 0.0001 or 0.9999. It'll be amazingly close to either 0 or 1. And so the M step, so this is pretty much guessing whether each document is in cluster 1 or cluster 0, and then sort of using formulas that are very similar to maximum likelihood estimation for naive Bayes. Okay. Cool. Are there, and if some of these equations don't look that familiar to you anymore, so go back and take another look at what you saw in naive Bayes, which, and hopefully you can see the links there as well. Questions about this before I move on? Okay. Oh, and of course, the way I got these equations was by churning through the machinery of the EM algorithm, right? I didn't just write these out of thin air. The way you do this is by writing down the E step and the M step for this model, and then the M step, saying derivatives equals to 0 and solving for that. So that's how you get the M step and the E step. So So the last thing I want to do today is talk about the factor analysis model. And the reason I want to do this is there's sort of two reasons, I guess. One is, factor analysis is kind of a useful model. It's not as widely used as mixtures of Gaussians and mixtures of naive Bayes, maybe, but it's sort of useful. But the other reason I want to derive this model is that there are a few steps in the math that are more generally useful. In particular, when I describe factor analysis, this will be an example in which we'll do EM, where the latent random variable, where the hidden random variable Z is going to be continuous valued. And so some of the math we'll see in deriving factor analysis will be a little bit different than what you saw before. And they're just it turns out the full derivation for EM for factor analysis is sort of extremely long and complicated. I sort of won't inflict that on you in lecture today, but I will still be writing more equations than you'll see me do in other lectures, because there are sort of just a few steps in the factor analysis derivation that are sort of particularly illustrative. So to actually motivate the model, I generally contrast this to the mixture of Gaussians model, right? So for the mixture of Gaussians model, which is our first model, we had that, I actually motivated it by drawing a data set like this, right? That what if you have a data set that looks like this, right? So this was a problem where n is two-dimensional, and you have, I don't know, maybe 50 or 100 training examples, whatever, right? And I said, maybe we want to, given an unlabeled training set like this, maybe you want to model this as a mixture of two Gaussians. Okay? And so mixture of Gaussian models tend to be applicable where m is larger, and often much larger than n, where the number of training examples you have is at least as large as, and usually much larger than the dimension of the data. What I want to do is talk about a different problem where I want you to imagine what happens if either the dimension of your data is roughly equal to the number of examples you have, or maybe the dimension of your data is maybe even much larger than the number of training examples you have. Okay, so how do you model such very high dimensional data, which you will see sometimes, right? If you run a plant or something, you run a factory, maybe you have 1,000 measurements all through your plant, but you only have 20 days of data, so you can have 1,000 dimensional data, but 20 examples of it only. So given data that has this property, and again, you're given a training set of m examples, well, what can you do to try to model the density of x? So one thing you could do is try to model it just as a single Gaussian, right? So never mind mixtures of Gaussians. Let's say you try to model it as a single Gaussian. You can say x is distributed with mean mu and parameter sigma, where sigma is going to be an n by n matrix. And so if you work out the maximum likelihood estimate of the parameters, you find that the maximum likelihood estimate for the mean is just the empirical mean of your training set. Right, so that makes sense. And the maximum likelihood estimate of the covariance matrix sigma will be this. Right? But it turns out that in this regime, where the data is much higher dimensional, where the data's dimension is much larger than the number of training examples you have, if you compute the maximum likelihood estimate of the covariance matrix sigma, you find that this matrix is singular. By singular I mean that it doesn't have full rank, or it has 0 eigenvalues, so it doesn't have. Hope at least one of those terms makes sense. All right, and I guess another saying is that the matrix sigma will be non-invertible. And just in pictures, one concrete example is if if n equals m equals 2, if you have two-dimensional data, and you have two examples. So if you have two training examples in 2 dimensions, so this is x1 and x2, this is my unlabeled data. If you fit a Gaussian to this data set, you find that, you remember I used to draw contours of Gaussians as ellipses, right? So this is, so these are examples of different contours of Gaussians. You find that the maximum likelihood estimate Gaussian for this corresponds to, a Gaussian where the contours are sort of infinitely thin and infinitely long in that direction. Okay, so the contours will sort of be infinitely thin, right, and stretch infinitely long in that direction. And another way of saying this is that if you actually plug in the formula for the density of a Gaussian, which is this, you won't actually get a nice answer because the matrix sigma is non-invertible, so sigma inverse is not defined, and this is 0. So you also have sort of 1 over 0 times e to the some inverse of a non-invertible matrix. So this is sort of not a good model. So let's see if we can do better, right? So given this sort of data, how do you model P of x? Well, well, one thing you could do is constrain sigma to be diagonal. Right, so you have a covariance matrix, X is. Okay, so in other words, you're going to constrain sigma to be this matrix, right, with zeros on the off diagonals. I hope this makes sense. These zeros are written down here to denote that everything off the diagonal of this matrix is a 0. So the maximum likelihood estimate of the parameters will be pretty much what you'd expect, right? And in pictures, what this means is that you're modeling the distribution via Gaussians whose contours are axis aligned. So that's one example of a Gaussian where the covariance is diagonal. And here's another example, right? And so here's a third example. But all 3 of these are examples of Gaussians where the covariance matrix is off diagonal. Okay, and I don't know, you could do this in model P of X, but this isn't very nice because you've now thrown away all the correlations between the different variables. So the axes here are like x1 and x2, right? So you've thrown away, you're failing to capture any of the correlations or the relationships between any pair of variables in your data. Yeah.
Yeah, so can you say again, what does it do if it's all diagonal?
Say it again?
If the covariance matrix is diagonal, what does that do again? I didn't quite understand what the examples mean.
Oh, okay. So these are the contours of the Gaussian density that I'm drawing, right? So let's see. Suppose the covariance matrix is diagonal, then you can ask what is P of X, parameterized by mu and sigma, right? If sigma is diagonal, and so this would be some Gaussian bump, right? So remember oh boy, I draw this really badly, but in 2D, the density for Gaussian is like this bump shaped thing. Right, so this is the density of a Gaussian. Wow, this is a really bad drawing. Where those are axes x1 and x2, and the height of this is P of X. And so those figures over there are the contours of the density of a Gaussian. So those are the contours of this 3D shape.
I know these are contours. What's special about these contours? What makes them different than sort of a general
I see.
covariance matrix?
Oh, okay, sorry. Oh, they're axis aligned. So the the main, let's see, so I'm not drawing a contour like this, right, because the main axes of this are not aligned with the x1 and x2 axes. So this will correspond to Gaussian where the off diagonals are non-zero. Right. Okay, cool. Yeah. Okay, so let's see. You could do this. This will sort of work. It turns out that with as few as 2 training examples, you can learn a non-singular covariance matrix. But this is sort of, but you've thrown away all the correlation in the data. So this is not a great model. It turns out you can do something. Actually, we'll come back and use this property later. But it turns out you can do something even more restrictive, which is you can constrain sigma to be equal to sigma squared times the identity matrix. So in other words, you can constrain it to be diagonal matrix, and moreover, all the diagonal entries must be the same. And so for the cartoon for that is that you're constraining the contours of your Gaussian density to be circular. Okay, and this would be sort of an even harsher constraint to place on your model. So, excuse me, either of these versions, diagonal sigma or sigma being the sort of constant value diagonal, are maybe overly strong assumptions. Right? So if you have enough data, maybe you'd like to model just a little bit of a correlation between your different variables. So the factor analysis algorithm, the factor analysis model is one way to attempt to do that. So here's the idea. So this is how the factor analysis model models your data. We're going to assume that there is a latent random variable. It just means hidden random variable z. So z is distributed Gaussian with mean 0 and covariance identity, where z will be a d-dimensional vector now, and d will be chosen so that is lower than the dimension of your axis. Okay. And now I'm going to assume that x is given by well, let me write it like this. Each xi is distributed. Actually, sorry, I'm just I'm going to assume that conditioned on the value of z, x is given by another Gaussian with mean given by mu plus lambda z and covariance given by a matrix psi. So just to say this, just to say the second line in an equivalent form, equivalently, I'm going to model x as mu plus lambda z plus, a noise term epsilon, where epsilon is Gaussian with mean 0 and covariance psi. And so the parameters of this model are going to be a vector mu, which is n-dimensional, a matrix lambda, which is n by d, and a covariance matrix psi, which is n by n. And I'm going to impose an additional constraint on psi. I'm going to impose a constraint that psi is diagonal. Okay. So that was the formal definition. Let me actually sort of give a couple of examples to make this more concrete. So let's give one concrete example. Suppose z is one-dimensional and x is two-dimensional. So let's see what this model. Let's see a sort of a specific instance of the factor analysis model and how we're modeling the joint, the distribution over x. So what this gives us in terms of a model for p of x. Right. So let's see, for this model too, let me assume that lambda is 2, 1, and psi, which has to be a diagonal matrix, remember, is this. Okay? So z is one-dimensional, so let me just draw a typical sample for z, right? So, if I draw zi from a Gaussian, so that's a typical sample for what z might look like. And so I'm going to enumerate, I'm going to call this z1, z2, z3, and so on. If this really were a typical sample, the order of the z's would be jumbled up, but I'm just ordering them like this just to make the example easier. Okay, so here's a typical sample of random variable z from a Gaussian distribution with mean 0 and covariance 1. And for this example, let me just set mu equals 0. It's 2 by just so it's easier to talk about. So lambda times z, right? We'll take each of these numbers and multiply them by lambda, and so you find that all the values for lambda times z will lie on a straight line, right? So for example, this point here would be 1, 2, 3, 4, 5, 6, 7, I guess. So if this was z7, then this point here would be lambda times z7. And now that's the number in R2, because lambda is a 2 by 1 matrix. And so what I've drawn here is like a typical sample for lambda times z. And the final step for this is, what's the typical sample for x look like? Well, x is mu plus lambda z plus epsilon, where epsilon is Gaussian with mean mu and covariance given by psi. Right? And so the last step, to draw a typical sample for the random variables x, I'm going to take these lambda z's. Well, these are really same as mu plus lambda z, because mu is 0 in this example. And around this point, I'm going to place an axis-aligned ellipse. Or in other words, I'm going to create a Gaussian distribution centered on this point. And this ellipse I've drawn corresponds to one of the contours of my density for epsilon, right? And so if you imagine placing a little Gaussian bump here, and so I'll draw an example from this little Gaussian, and let's say I get that point, right? I'll do the same here. So on. So I draw a bunch of examples from these Gaussians, and the orange points I drew will comprise the typical sample for what the distribution of x is under this model. Okay? Yeah.
Would you add
Say that again?
Do you add mu to that?
Oh, yes, you do. And in this example, I set mu to go 0, 0, just make it easier. If mu was something else, you take the whole picture and you sort of shift it, to whatever the value of mu is. Yeah.
So there's a horizontal line right there with the z's. What do the x's what does that line x's correspond to?
Oh, so this is z is one-dimensional. So here I'm plotting a typical sample for z. So this is like 0. So this is just the z-axis, right? So z is one-dimensional data. So this line here is like a plot of a typical sample of z values for z. Okay. Yeah.
You actually data points by x, right? And the actual data in the training examples.
Yes, right.
So projecting them into that.
Let's not talk about projections yet, but yeah, right. So these beige points, so that's like x1, and that's like x2, and so on, right? So the beige points are what I see, and so I'm sort of in reality, right, all you ever get to see are the x's, but just like in a mixture of Gaussian's model, I told a story about, well, we'll imagine the data came from two Gaussians, and it was this hidden random variable z that led to the generation of the x's from two Gaussians. So in the same way, I'm sort of telling a story here, in which all the algorithm actually sees are the orange points, but we're gonna tell a story about how the data came about, and that story is what comprises the factor analysis model. Okay. So one other way to see the intuition in this model is that we're going to think of the model one way, just informally, not formally, but one way to think about this model is you can think of this factor analysis model as modeling the data coming from low dimensional subspace, more or less. So the data x here lies approximately on 1D line, and then plus a little bit of noise, plus a little bit of random noise, so the x isn't exactly on this 1D line. That's one informal way of thinking about factor analysis. So, not doing great on time. Well, let's do this. So let me just do one more quick example, which is, in this example, let's say z is in R2 and x is in R3, right? And so in this example, z, your data z now lies in 2D. And so I'm going to draw this on a sheet of paper, okay? So let's say the axes of my paper are the z1 and z2 axes. And so, here's a typical sample of point z, right? And so we'll then take the sample z. Well, actually, let me just draw this here as well. Right, so this is a typical sample for z drawn on the z1 and z2 axes. And I guess the origin would be here, rather, whatever. So centered around 0. And then we'll take this and map it to mu plus lambda z. And what that means is, if you imagine that the 3D space of this classroom is R3, what that means is to take this typical sample of z's and we'll map it to position in free space. So take the sheet of paper and move it somewhere at some orientation in 3D space. And the last step is you have x equals mu plus lambda z plus epsilon. And so you would take this set of points, which are lying in some plane, in our 3D space, you add a little bit of noise to these. And the noise will sort of come from Gaussians that are axis aligned. Okay, so you end up with a data set that's sort of, like a flat pancake with a little bit of fuzz on your pancake, right? Lying a little bit off your pancake. So that's the model. Let's actually talk about how to fit the parameters of the model. Okay. In order to describe how to fit the model, I'm actually going to need to rewrite Gaussians in just a very slightly different way. So in particular, let's say I have a vector x. I'm going to use this notation to denote partitioned vectors, right? x1, x2, where if x1 is, say, an r-dimensional vector, and x2 is, say, an s-dimensional vector, and x is an r plus s-dimensional vector. Okay, so I'm going to use this notation to denote just, like taking a vector and sort of partitioning the vector into two halves. The first r elements followed by the last s elements. So let's say you have x coming from a Gaussian distribution with mean mu and covariance sigma, where mu is itself a partition vector. So break mu up into two pieces, mu1 and mu2. And the covariance matrix sigma is now a partitioned matrix. Okay, so what this means is to take the covariance matrix sigma, and I'm going to break it up into 4 blocks, right? And so the dimensions of this is, there'll be r elements here, and there'll be s elements here, the s elements here, and there'll be r elements here. So for example, sigma 1, 2 will be an r by s matrix. Right, so it's r elements tall and s elements wide. So this Gaussian that I've written down is really a joint distribution over lots of variables, right? So x is a vector, so this specifies a joint distribution over x1 through x, over xn, or over x of r plus s. We can then ask, what are the marginal and conditional distributions of this Gaussian? So for example, with my Gaussian, I know what p of x is, but can I compute the marginal distribution of x1? Right, and so the p of x1 is just equal to, of course, integrate out x2, p of x1, comma x2, dx2. And if you actually perform that distribution, that computation, you find that p of x1, I guess, is Gaussian with mean given by mu1 and sigma 1, 1. Right, so this is sort of no surprise. The marginal distribution of a Gaussian is itself a Gaussian. And you just take out the relevant sub-blocks of the covariance matrix and the relevant sub-vector of the mean vector mu. You can also compute conditionals. So you can ask, what is p of x1 given a specific value for x2? Right? And so the way you compute that is, well, the usual way, p of x1, comma x2, divided by p of x2, right? And so you know what both of these formulas are, right? The numerator, well, this is just your usual Gaussian. Your joint distribution over x1, x2 is a Gaussian with mean mu and covariance sigma, and this, by that marginalization operation I talked about is that. So if you actually plug in the formulas for these two Gaussians, and if you simplify, the simplification step is actually fairly non-trivial. If you haven't seen it before, this would actually be, you can try to do it. This would actually be somewhat difficult to do. But if you if you plug in these two formulas for Gaussian and, you know, and simplify that expression, you find that conditioned on the value of x2, x1 is the distribution of x1 conditioned on x2 is itself going to be Gaussian. And it will have mean mu of 1 given 2 and covariance sigma of 1 given 2, where, well, so if after simplification and derivation that I'm not going to show, the formula for mu of 1 given 2 is given by this. And okay, the sigma of 1 given 2 is given by that. Okay, so these are just useful formulas to know for how to find the conditional distributions of a Gaussian and the marginal distributions of a Gaussian. And I won't actually show the derivation for this. So, sure. So this one on the left, mu of 1 given 2 equals mu1 plus sigma 1, 2, sigma 2 to inverse times x2 minus mu2. And this is sigma 1 given 2 equals sigma 1, 1 minus sigma 1, 2, sigma 2 to inverse sigma 2, 1. Okay? These are all also on the lecture notes. Shoot. Not doing as well as I was hoping to on time. Well, actually, I think that's. Okay. So it turns out, I think I'll skip this in the interest of time. So it turns out that, well, so let's go back and use these in the factor analysis model, right? It turns out that you can go back and, do I want to do this? Yeah, I kind of need this. Well, fine. So let's go back and figure out just what the joint distribution factor analysis assumes on z and x's. Okay. So under the factor analysis model, z and x, the random variables z and x, have some joint distribution given by, I'll write this vector as mu zx and some covariance matrix sigma. So let's go back and figure out what mu zx is and what sigma is. And I'll do this so that we'll get a little bit more practice with partition vectors and partition matrices. So just to remind you, right, we have that z is Gaussian with mean 0 and covariance identity, and x is mu plus lambda z plus epsilon, where epsilon is Gaussian with mean 0 covariance psi. Okay, I'm just writing down the same equations again. So let's first figure out what this vector mu zx is. Well, the expected value of z is 0, and again, as usual, I'll often drop the square brackets around here. And the expected value of x is, well, it's the expected value of mu plus lambda z plus epsilon. So, these two terms have 0 expectation. And so the expected value of x is just mu. And so that vector mu zx, right, in my parameter for the Gaussian, this is going to be the expected value of this partition vector given by this partition z and x. And so that would just be 0 followed by mu. Okay, and so that's a d-dimensional 0 followed by an n-dimensional mu. Let's now go and work out what the covariance matrix sigma is. So so the covariance matrix sigma, if you work out definition of a partitioned so this is into a partition matrix. Okay, so the covariance matrix sigma will comprise 4 blocks like that. And so the upper leftmost block, which I write as sigma 1, 1, well, that uppermost left block is just the covariance matrix of Z, which we know is the identity. I'm just going to show you briefly how to derive some of the other blocks, right? So sigma 1, 2, that's the upper, oh, actually, excuse me, sigma 2, 1, which is the lower left block. That's E of x minus EX times Z minus EZ. So x is equal to mu plus lambda Z plus epsilon. And then minus EX is minus mu, and then times Z, because the expected value of Z is 0, right? So that's equal to 0. And so if you simplify, or if you expand this out, plus mu, minus mu cancel out, and so you have the expected value of lambda, oh, excuse me, right, ZZ transpose minus the expected value of epsilon Z. Is equal to that, which is just equal to lambda times the identity matrix. Okay? Does that make sense? Because this term is equal to 0. Both epsilon and Z are independent and have 0 expectation, so the second term is equal to 0. So the final block is sigma 2, 2, which is equal to the expected value of mu plus lambda Z plus epsilon minus mu times right, which is equal to, and I won't do this, but this simplifies to lambda lambda transpose plus psi. Okay? So, putting all this together, this tells us that the joint distribution of this vector Zx is going to be Gaussian with mean vector given by that, which we worked out previously. So this is the mu Zx that we worked out previously. And covariance matrix given by that. Okay? So, in principle, let's see. So the parameters of our model are mu, lambda, and psi. And so in order to find the parameters of this model, we're given a training set of m examples. And so we like to do a maximum likelihood estimation of the parameters. And so in principle, one thing you could do is you can actually write down what p of xi is. And right, so p of xi, xi is actually, the distribution of x, right? If again, you can marginalize this Gaussian. And so the distribution of x, which is the lower half of this partition vector, is going to have mean mu and covariance given by lambda lambda transpose plus psi. Right? So that's the distribution that we're using to model p of x. And so in principle, one thing you could do is actually write down the log likelihood of your parameters, right, which is just the product over I guess the sum over I log p of xi, where p of xi will be given by this Gaussian density, right? And I'm using theta as a shorthand to denote all of my parameters. And so, I mean, you actually know what the density for a Gaussian is, and so you can, say p of xi is this Gaussian with mean mu and covariance given by this lambda lambda transpose plus psi. So you can actually write down the log likelihood of your parameters as follows, and you can try to take derivatives of your log likelihood with respect to your parameters and maximize the log likelihood. Right. It turns out if you do that, you end up with sort of an intractable optimization problem, or at least one that you end up with a optimization problem that you will not be able to find an analytic sort of closed form solution to. So if you say, my model for x is this, we'll try to do maximum likelihood parameter estimation, you won't be able to find the maximum likelihood estimate of parameters in closed form. So what I would have liked to do is, So in order to fit parameters to this model, what we'll actually do is use the EM algorithm, in which in the E step, right, we'll compute that. And this formula looks the same, except that one difference is that now z is a continuous random variable. And so in the E step, we'll actually have to find the density qi of zi, where the E step actually requires that we find the posterior distribution, of a density to the random variable zi. And in the M step, we'll then perform the following maximization, where, again, because z is now continuous, we now need to integrate over z. Okay, we're in the M step now because zi is continuous. We now have an integral over z rather than a sum. Okay, so hoping to go a little bit further in deriving these things, but I don't have time today. So we'll wrap that up in the next lecture. But before I close, let's check if there are questions about the whole factor analysis model thing. Okay, so when we come back in the next lecture, I will wrap up this model, and particularly I want to go a little bit deeper into the E and M steps, since there are some tricky parts for the factor analysis model specifically. Okay, I'll see you in a couple of days.